in acylation,
Okay.
and then obviously I got rid of the ketone,
Mm-hmm.
and then did a sulfonation as a blocking group so I could do the bromine on a ortho.
Yep.
Did you need to do that?
Yes. So yeah.
Okay, gotcha. Okay, so that was pretty straightforward.
Mm-hmm.
This second one, I kind of had to remember things from the last chapter a little bit.
Yep. For that first
Okay,
hydration step. Yeah.
so yeah, I just did it like a normal acid catalyzed hydration,
Yep. That works. There's
and then
no regiochemistry you need to worry about for this. So yeah.
an oxidation with chromic acid,
Yeah, that works. Yeah.
and
Anything
then
would
just
pretty
a
much work
normal
there.
primary um,
I
amide.
mean,
I
yeah.
mean, okay,
Yep.
gotcha, that makes sense. Yeah, that
So I
first
don't.
part I was like, what am I gonna do for this part? Well, that makes sense.
Yeah. So the last reagent should have been, what is it? This, I think. But yeah, other
Okay,
than that, yeah, as you said, those are the steps. Not
gotcha.
too complicated.
Dang, so yeah, just on A, then that kind of got me because
Yeah, I
I didn't
think,
even think about that fourth.
yeah,
Well, it
that's only
makes
going to be a
sense
couple
because
points off, I think. But
yeah,
yeah.
it makes sense because when I was looking at the sigma complex that I had with just those three, they all look pretty much the same, or in terms of
Hmm.
like stability. So I just wasn't sure. And then the way you drew it makes more sense that when you put it up there, you get the octets.
Yep.
But
Yeah.
yeah, it's what's funny is I missed that on my homework and then I missed it again too. So I
Cool.
probably deserve it. But anyways, thanks, man. Appreciate it.
Yeah, sure. All right. So what I'm going to do now, unless more questions come up, is I'm basically just going to work through the rest of the mechanisms questions for part 3. And yeah, we'll go from there. So let's see. We kind of went over, I guess I'll do all of part 2A right now. Pull that up just to make sure I'm on the right page, but yeah. So basically what you'll have is this right here. And you'll have, what's the structure look like originally? So it has this ether. I'm going to draw those lone pairs in just because we'll need them later. So it's going to happen, since it told us that it was going to be at that para position, the first step is basically going to be you have your nitro group. So we'll draw that out. Make it a little bent, even though it's not really bent. It says that positive charge. This will go here, push some electrons there. And the first step you'll get then will look like this. Then you have hydrogen here, positive charge there. And the nitro group is going to be right here, which does look like that. From now on, I'm just going to draw that as NO2 though, because that's not going to change. So looking at how this is going to work, the main part for this is you do have to draw that sigma complex, and there are going to actually be 4 different possible structures. So this is the first one. I'm just going to move it around the ring a little bit. So the next one is going to look like this. So you have this here, the positive charge is here. And we still then have the nitro group here with the hydrogen. The next one, and this is the one that's going to trick a lot of people, so do not be concerned if you miss this. And I just went over this kind of, but looking at this, you're actually, since you have those lone pairs, one of them can move down there, and you're going to get this structure. And now the positive charge is on oxygen. And the last thing you're going to have then is just going to be the other one if the charge kept moving around the ring. So I'll draw that out really quick. And for full credit, you did need all of these. And then basically for that last step, all that's going to happen is I'm going to use water. I think in the past we've used like the deprotonated form of the acid or whatever you want to use. But you then have that come and take that proton off. Over there. That goes back into a pi bond. Your final structure then is the product it asked for, which will be this. Okay. So there is part 2. Let's see the next one. Okay, so the next one, oh, I forgot to circle. The most stable one is going to be this one. And as I said earlier, the reasoning for that is everything has octet right now. So while the positive charge is still on the oxygen, it does, so it still has this lone pair I didn't draw. It has 1, 2, 3, 4, 5, 6, 7, 8 in that bond too. So it leads to having octet. Moving on then. The next one does want you to draw basically the product for, I guess, missing products. And so I'll just draw out the whole problem first, and we'll go over the steps. So it says first we're going to treat this with acid as well as your protecting group. And so looking at that, it also says that you're losing H2O, but that doesn't really mean anything here. The question just goes, which one does it add to? Aldehydes are actually more reactive than ketones, so I'm going to add it to the aldehyde group. I'm guessing it'll be common to add it to the other one as well. I'm not quite sure how many points will be taken off for that, but in theory that would also happen, but you'd expect the aldehyde to react first. So I'm just going to draw that out. Looks like that, and you still have the ketone over here. So what's going to happen next is you're just doing the Grignard's reaction. And so while this is protected, treating this with Grignard's, which is just a little propyl group here that it's adding. All you're going to do then is remember this carbon will attack right here. You're treating with water afterwards, so you will form an alcohol there. So you'll have this original chain. So that's there. This is now going to be an alcohol, and you now have this extra propyl group. And you're also then just going to deprotect, which is what the H2O will do as well. So I guess in the same step, you would technically have this still be O- after this step. By adding H2O, what you'll have is this. Okay, and so the next part just wanted you to write out the mechanism for this. And basically what that's going to end up looking like is, so for the formation of the acetal, I'm just going to use R and zoom in on that one area. If you have any more specific questions, let me know. Hopefully you should be able to see that the rest of this isn't really going to change that much. But basically what's going to happen is, so the first step, I'm just going to draw this. So this is the hydrogen. This is an R group with an oxygen here. The first step is one of the lone pairs of oxygen is going to pick up a hydrogen from the acid. So it was written as H+. I'm going to write this as hydronium. So this will just pick that up. What you'll now have is something that looks like this. The oxygen is positively charged. What's going to happen then is basically the protecting group So it looks like this. One of these oxygens, one of those lone pairs is going to come in, attack the carbonyl carbon, move that lone pair up. So what you now have is going to look like this. Technically, all of these could go both directions. But basically what you'll have is so it looks like this now. This oxygen is positively charged. What is going to happen is now water is going to come by. One of those lone pairs will take that hydrogen away, get rid of that positive charge. So now what you have is this. And basically the next steps of what's going to happen is you basically now are going to reprotonate the original oxygen that's on there. So it's going to take another hydrogen from the water. What that gives you is this. Let's try that going both directions. My bad. So now what's basically going to happen is, since this is positively charged, you're going to have one of the lone pairs of oxygen come here and force that off. So I'll add that lone pair, this will go there, this goes there. What you now have formed, and I'm kind of going to flip this orientation in space. We have an R group. Looks like this. Basically what's going to happen now is just you can have this oxygen attack here. When it does that, this lone pair, I forgot this is still positively charged. This will force that up there. What you now have then is going to be this. It's still positively charged now. All that's going to happen is water will come in, remove that hydrogen, and what you're going to have then is your protected group. And there you go. So there's that acetal formation. Let's see what's next. Yeah, so the next is just a couple synthesis questions. So I'll go over kind of how you're supposed to do those. The first one, it just says you're supposed to go from benzene. And once again, if anyone has questions, feel free to stop me. So it looks like this. That's our goal. What I'm going to do basically, I'm going to do acylation first, just because I know that. So it's going to be orthopara. It doesn't really matter which one. However, bromine is slightly deactivating, whereas an alkyl group is slightly activating. So I'm just going to start by adding that alkyl group. So to do that, I'm going to do acylation, Friedel-Crafts, so AlCl3, as well as this compound here. And what that's going to look like once it reacts will be this. And next, what I'm going to do, because right now this is actually withdrawing and a meta director, we're going to want to make it ortho-para-directing. So I'm going to do the Clemens introduction right now, the amalgamated zinc, and HCl. What we'll then get is this. So next thing I'm going to do, and I don't know if this is actually necessary, you would expect most of this product to be para though, and to make it so we can have that ortho product, what I'm going to do is protect it. So remember, if you just use fuming sulfuric acid, I'm just going to abbreviate that as fume H2SO4. That's going to do is add that protecting or blocking group, I guess, over there. So that looks like this. Basically then I'm gonna then add the bromine using Br2, Br3. Because that para position is blocked, it's going to have to add to the ortho position, just right here. Technically, it could be this one as well, but both of those in 3D space would be the same. And right now we're still blocked. So all I'm gonna do then is just treat it with dilute sulfuric acid. And what you'll get is this. So that is that one. The next one then is a little more complicated just because it pulls like kind of a older reaction you might not remember. But the first thing you have to do, so it wants you to go, I guess, from this with a cyclohexene to an amide here. And so basically you can see that there is this double bond there that is not present in your final compound. Also, in order to do this reaction, you're going to actually need to have a ketone present. So we'll have to first basically add a ketone to this alkene, and then we can work on the addition. And so all that's going to look like is I'm just going to use acid catalyzed, so H3O plus. Remember what that's going to do is make the reaction, basically it just adds an OH group at either position. I'm going to do it here. Next, you're going to have to oxidize this a little. So I'm going to use PCC. You could use anything you wanted. Not anything, I guess, but anything that is an oxidizing agent. That turns it into this. At that point, all you have to do is treat it with primary amine. And so what that's going to look like to form that product is H2N will be that functional group. Then that, as well as then water and acid. What this then gives you is that final product, which looks like this. Okay. Then just going to move on a little bit and do the last one, which is just the bonus. I guess it just wants to know which one is a stronger activator when comparing these two. So this and this. The correct answer should be this one. And the reason is, remember, this is one of those atoms that has a lone pair here that can be electron donating, donate into the ring, have more resonance stability. Whereas the other compound here is actually electron withdrawing based on how it's set up. So it can potentially withdraw that, have a slightly positive charge there. That is very unfavorable. So the correct answer would have been this one. And as long as you explained it with something of that kind of logic, you'd be fine. So all I'm going to do now is kind of just look through the practice exam and see how, or not the practice exam, sorry, your actual exam, and kind of just see which ones people struggled with. I'm not going to worry about naming ones here. If you have any questions about naming, feel free to ask Dr. Vickery. Let's see. So I guess I'll go over the synthesis ones. I think that's a good one. And so all of these do have, I guess not all of them, but some of them have multiple answers that you could have done letter-wise, and people will have to go back and look over these. But the first one I guess we'll look at is it wants you to form this from benzene. And so there are a couple ways of doing this. Basically, obviously you need to add a nitro group and a carboxylic acid. How that's going to look is one of your steps is going to have to be oxidizing this group all the way to be that carboxylic acid. But there are multiple ways of doing this. Since these are meta to each other, you could kind of do it in different orders. I'm going to do NO2 first because that is going to be a meta director. So all I'm going to do for that is, I guess the first step is going to be, I'm going to treat, I guess I'll start with benzene. So I'm just going to treat benzene with HNO3 and sulfuric acid. What that's going to do is it's just going to add a nitro group. Next, what I'm going to do is looking at the end goal for our compound. We do need to basically add a carbon before we can do that last step of oxidizing it all the way. So you're going to look for some sort of Friedel-Crafts acylation, the best compound for that. And you could do alkylation or acylation, doesn't really matter, but it would save a step if you did alkylation here because you wouldn't have to reduce that down with Clemmensen reduction. So I'm going to do next is just treat this with ethyl chloride, or sorry, propyl chloride, which in the key is written as this. So apologize for that handwriting, but what this will look like then is you're just adding that group to the meta position. I'm going to draw it over here just in the interest of space, but that's the same as where it's written in the key. You basically then added this group. All you're going to do then, if you do this set of steps, is you're next going to oxidize it. Remember, that's the dichromate one. So Na2, Cr2O7, as well as the sulfuric acid and water. I'm not going to write that all out right now, though. And all that will do then is just transform it into this. And there we go. So that's one of those. I'm probably, unless I get a ton more questions, just do a couple more of these. How many are left? Yeah, there's only one more synthesis one, it looks like. So I'm just going to work through that one and then we'll call it a day a little early. So let's see. This one wants you to form this from benzene. And so basically, you can see that there's a nitro group here as well as the hydroxyl group. There are a couple of different ways of doing this. Basically, to get the hydroxyl group on, you're going to have to do that elimination addition reaction at some point. Then for the amine here, you're going to have to add a nitro group and then reduce that down. And we learned ways of doing both of those things. So just kind of have to think about where things are going to add. The way I'm going to do this is I'm going to first just add a bromine. So this is going to be Friedel-Crafts bromination, I guess. So just add a bromine. I'm going to add it to the bottom just because that's how it's drawn. The next step then is this right here. The bromine is an ortho-para-director. So you might as well just add the nitro group at this point too. And so what I'm going to do for that is you're just using HNO3 and H2SO4. That's going to look like this. So you have that group there. Then there's a couple ways you could go from here to do the elimination substitution. Basically, I'm just going to do NaOH in heat. And what that is going to do then is after you also add acid, so H3O plus, which is I think written as a separate step on this, but if you skip that, you'd probably be okay. What you'll get is this. And then lastly, you just need to reduce down the NO2 to amide or amine, sorry. And so we're just going to do zinc and HCl. When you do that, that will make it your final product. And then the OH group is down here. And that is all. So unless there are any more questions, I am going to call this a day. And yeah, thanks for stopping by for those of you that came. And yeah, have a good one.